Yes. Okay. Assignment 3 is out there for you. Put out there about 5 minutes ago. So this one.
Can you turn your mic on, please?
Pardon? When I got it first, now it's on. Okay. All right, now we go. So assignment 3 is out there for you. This one will take you a little longer. Basically, it says model. A little longer. It says model the front part of Boehner, right? So you've got all the chairs and things like this, the front of Boehner. I'm sorry, the front of Kemper. It should be the front of Kemper. Okay. So they got all those new, nice, beautiful, ugly chairs in there that all look identical, right? This is the part of the problem. I want you to look at many of the things that are the same, right? And if the things are the same, we should be able to do them fairly easily with the computer systems. Okay? My advice is start simple. Don't try to write up the entire thing at once. Start with one piece of furniture and do it. Go ahead.
You have to build that display thing of all the computers.
No, you don't have to do that. You don't have to do the bicycle in front either. Okay. I'm trying to get you to do some polygons, some really simple other things, etc. Okay. And you can do as much as you want, right? The floor pattern would be fun to do.
You said the front of Kemper. Do you mean the lobby?
The lobby of Kemper, yeah. The front and the lobby of Kemper. Okay. The windows you can model very easily, right? By just assuming they're not there. Okay, which is quite frequently the case in graphics. We model windows very easily, okay, and things like that. So, I mean, I'm not looking for hugely complex here. I also said you've got to design what we call a Cessna Viewer, right? So you can fly into things and back and in and out, and you can arrange the buttons anyway. Most of us have you go forward when you press the left button, you go back when you press the right. Some people do the zooming with the wheel. Left or right kind of turns your plane left or right when it flies around, etc.
What perspective are you looking at that lobby from? Because you mentioned windows as well. Are you standing right at the door?
Yeah, you can stand at the door and inside, right? So you should be able to fly inside the lobby and around and back out, etc. Okay?
Should you avoid jamming in the furnitures and stuff?
No.
Oh, you can go through it.
Yeah, you should be able to fly through things very easily. Yeah.
No, I mean,
yeah.
If to avoid it would be harder.
No. Collision avoidance is collision detection is one of the very difficult problems to do when you're flying around things. Still, one of the very difficult problems to do, and it's not too hard to figure out why. That it's you have to test yourself against everything. Right? Each frame you go, you have to test yourself against everything. So we have all kinds of weird ways to avoid collision.
How are we defining the boundary of the lobby? Because there's hallways, and then there's always the back side.
Let's just say as much as you could see in the lobby. Okay, I'm not looking for all the hallways adjoining the lobby or the dean's office or anything else. Okay, I'm more or less thinking about the lobby. You could easily do it so there's a hallway there. Okay. But you don't need to put all the doors and door handles and everything on the hallway, etc. Okay. You'll find this looks daunting, but as you get going, it actually is going to go pretty quick. Okay, go ahead.
Do you want us to get our data managers and actually do everything at scale, or?
Yeah. Lasers, you can put your lasers up on the wall. The blueprints actually are on file somewhere. You can probably find that by going into the dean's office. If you want, write me email and I'll see if I can find those for you. Okay. I don't think there's a drinking fountain in this one. Usually I have you do the stream of water coming out of the drinking fountain too, but that's all right. Okay. Now, I mean, fortunately there are, I think like 16 chairs, right, in the lobby now of these god-awful looking chairs that they bought. They're all identical, right? So you should be able to do these very easily by making a basic chair routine, draw routine, and then transforming it. That's the whole purpose of what Ken's talking about here, okay, is learning how to transform these things. Go ahead.
And then second story, like stairs?
Yeah, there's stairs there, isn't there? Right? Yeah. How about that? Okay. And all those stairs look remarkably the same. Okay. And they just happen to be a few inches above one another. And they do curve. Yeah. That's another thing. Okay. It's true. Okay. Go ahead.
You need lighting?
And you need lights. Yes. Of course. Of course. Pardon?
Different material properties?
Different material properties, right, if necessary. Okay, again, work your way up to this, right? Don't start worrying about the, the exact material properties of something first. Do the geometry first, right? Then put the properties in.
Is this a right button to increase the forward speed or backward speed? Do you want it to be like the increase in the depth or just?
I don't care. Whatever you do. However you want to fly your own thing. You might suggest to when you turn it in, you might give the reader some indication of how to use the mouse to fly your thing. Yeah. I mean, counterintuitive probably isn't good. I mean, backwards being usually means backwards, right? And But it is the case with the mouse that you can do. It's as if you've got a joystick in the plane, right? You pull it back, the plane should go up. Pull it forward, the plane should go down, etc. Okay? Go ahead.
Can I combine the various D with the mouse?
Can you combine?
The key or the...
Sure. Well,
Yes.
yeah, so you're, okay. Sure. Yeah. And you can even shoot things off into the scene if you like. That's okay. Right. Right. The dean might enjoy that with Painter Hall. Yeah. That's not a required part of the assignment, though. Yeah, no collision detection, no anything like that. As far as I'm concerned, you can fly through the chairs. The near-far clipping should take care of most of this for you. Okay, when you fly through things, or the near clipping should take care of most of it for you. The pattern on the floor, by the way, I didn't learn. I was on the design committee for that building. I didn't learn what the pattern on the floor in Kemper meant. If you've all seen the interesting pattern on the floor, it's 17.5 degrees off, or the angles are 17.5 degrees. And after the building was built, they had a meeting of the Architectural Society of America here. And so they stood up and they said what all the, the red colors on the outside of the building meant, and the turquoise, what it meant. And the 17.5 degrees is evidently the furrows in the farm fields here are plowed 17.5 degrees off north-south. And so this 17.5 degrees was to represent the agricultural heritage of the campus, well, along with the building. Okay, so this is, I had no idea when we were making the building that this is what we were doing, but that's what there. So, I mean, make it as realistic as you can. You'll find, once you get going with this thing, you'll find that almost everything in that building there are many things that are identical, right? All you need to do is transform them just a little bit, okay? And that's what these systems are good at, is transforming them, okay? So, one more?
Do we need to texture stuff?
You need to texture stuff. That's up to you. You'll certainly be texturing them on the next assignment. Right.
So, and what do the colors mean?
And pardon?
And what do the colors mean?
What do the colors mean?
We can't work on
Oh, the colors, I don't know. All I know is the 17.5 degrees. Right, that's all I know. Okay? I mean, when we make buildings and we do it in graphics, what we do is we run them with a camera and start shooting, If you want to make the dean's nameplate look realistic, you shoot the dean's nameplate, you go into Photoshop, cut it out, and then you texture it onto a rectangle and you put it up there and it looks like the dean's nameplate. Right? I mean, we do this all the time. Okay? So, you know, there will obviously be other questions as we go along here. And I've given you almost 3 weeks to do it. So, you know, it's a substantial project. So today what I want to do is show you kind of how, I want to show you a small system that sometimes we have this class do as a project, but I want to show you a small system that was generated about 1977 and is still used. The essentials of it are still used today in many, many animation systems. And you should realize by now that hard coding a lot of these things, we don't hard code them. We usually have a file with all of our polygons in them, okay? And we read these files in. That way we can use an editor to edit the polygon description and not have them all hard coded in our programs. But we can read polygons in. And most systems do it that way. They have some sort of a file storage system where they put out there all the information about a polygon, which may include textures, which may include color information, which may include a bunch of stuff, okay? But in general, files typically contain some kind of polygons and a set of points, right? Let me try once more. Something like this, okay? They contain a word, a keyword like polygon, and some kind of points, right, associated with them. And what these files, all this thing is a square, okay? One unit on a side, starting there, there, and there. These are these points with z equal to 0. All right, and they have various commands to do this. So one command, these are command line commands, might be polygon A, something like this. You could type this in on a command line that would generate you a file of this type. Okay? These are the simplest ones. You could type this in on a command line, generate a file of this type. So this is going to be really set up for Unix files that we can put a whole bunch of commands like this. So you could do another poly B. Something like this, and now you have z equal to 1 in this poly B. Okay, go ahead.
Could you just polygon B is polygon A plus something, or
you could do that too. Generally, what I'm going to write out is just these simple commands to generate these. Right. So here all you've done, I'll assume, is you generate a file named A, okay, which contains the word poly and these points in it. This one generates a file named B, okay. And then you start doing this. And what I'm going to say is the files normally contain much more than this. Okay, they contain color, they contain material properties, all those 10 variables you have to put in. They can contain texture, they can contain texture coordinates, they contain all kinds of stuff, okay? We had one that had 101 different things that it actually contained, okay, to describe an object. Okay, so these files can get pretty voluminous, but if they look like this, you can actually edit them, which is kind of clever. But there's some other commands that you can do pretty easily on these files. Okay, so this one says transform A by a little code here, z translating by z by 1 unit. Okay, and what this does is, I mean, it's pretty simple. It sets up this matrix like this, which is the z translation of 1. Okay, if you remember this matrix, sets this up and multiplies this times every point in the little file you have. Okay, so when you get done here, A probably should be equal to B when you get done with this command. Okay, and you can set up all different kinds of these things, these transforms here. You can set up rotations. You can set up whatever, and it gives you a little file, right? And you could set up a lot of them. You could say transform A, z translate by 1, y translate by -3. Okay? and this sets up two matrices, multiplies them together, etc. And you get out another file, or you modify this file A. Okay, and many people built up these systems. Okay, effectively, when you go into Maya today or any one of these animation systems, and you do modeling, you're building up one of these files. Okay, this is about as simple as it gets, but it turns out these are the basis for most of these, and it sets up a set of commands that it can reproduce, right, in order for you to build up your objects. Right, now these commands, I could put them in a Unix script file and just say execute them, right, and I could build these objects up. And so by editing these commands, right, I could actually build some fairly complex objects up. Okay, the most complex I ever did were some 1903 railroad cars, right, which had about, I don't know, 2,000 commands in order to make them work. However, once you model one of the boards on the side of a railroad car, right, the rest of the railroad car contains those boards also, so all you have to do is translate them around. Okay, there's another command called create. C from A, let's do from B by Z translate of a -2. Okay? This one says create a new file called C starting from B, right? Take all the things in B and translate it by -2 in the Z direction. Okay, all these can be set up using matrices. So this command is just like the transform command except it creates something new. Right, leaves the original alone. All right. Okay, and you can use these sets of commands to build things very nicely. There's also other commands that we use. Extrude. Okay. Call it something D from A by 2 units, and what this does is it takes A, which is a square, and makes a cube object like this, where this is 2 units on a side. So it takes A and moves it back. Great for making table legs, right? Things like this. All you do is make a little square up at top. You say extrude it, right? And you get 6 polygons that make up this table leg. It's great for making tabletops and things like this. Just say extrude, and you get these things back. But you can make up fairly complex things here, and so let me start here. Polygon, square, -1, -1, 0. I'll do 0. -1, 1, 0, 1, 1, 0, 1, -1, 0. Okay, something like this. So here's my original square. I'm going to say transform square Z translate it 1 on the front. Okay. Now I'm going to say create back from square by Z translating it a -2. Hang on, let me write all these things down. Create left from square, Y rotate, rotate around the Y-axis, -90. Here's create right from square, Y rotate 90. Create bottom from square, X rotate 90. Create top, well, this has some fun, from bottom, Y translate 2, and let's say assemble square, top, bottom, left, right, back, into something called cube. Okay? Now you see what I've done with all these things? What I've done is I've taken my square, see if I can draw it, taken my square and I've actually rotated it out 1 unit, okay, out here, or translated it out 1 unit on the Z, okay. I then created a back, which is back here, by taking this thing and translating it backwards, okay. I then have created a left square by taking this front square and rotating it 90 around the y-axis, which gets me this guy over here. Okay? Like this. You see what's happening? Right? And when I've done with this, I've generated, oh, let's see, the fun, let's see. The bottom, I took the square and I rotated it around the x-axis 90 degrees, so it ended up on the bottom. And then to create the top, I took the bottom and translated it upward too. Okay? This is all fun and good, fun and games here. But what have I done here in reality? I now have taken 6 squares, okay, and assembled them into a cube. And all this assemble is cat. I've just taken these files and I've catted them all together. Okay, nothing more. That's all this assembled in and named it a new file. Okay? Well, now I'm going to have more fun, and you'll start to see the power of these things, is I'm going to say create. I need longer chalk. Cube 1 from cube by an x translation of 2.5, say. Create cube 2 from cube, an x translation of a minus 2.5, and assemble cube 1, and cube 2 into 3 cubes. Like this. Now can you see what I've done? All right, I have a cube, and I've translated it 2.5 in the x direction, so that's bigger than the width, so I end up with this over here. All right. And then I got another one. I do it minus in, let's see. No, it's got to be this way. Like that. That's what I've done. Still with me? Okay, and now all of a sudden, these are files, right? And how many squares does this file have in it? How many polygons does this one have in it now? I think probably about 18 in here. Okay. All right, so now I'm going to create 3 cubes 1 from 3 cubes by a y translation of 2.5. I'm going to create 3 cubes 2 from 3 cubes with a y translation of a minus 2.5. And then I'm going to assemble 3 cubes 1, 3 cubes 2 into 9 cubes. Do I have to draw the picture of this one, or you got the idea? Okay, I'm going to do one more, and I'm going to do create 9 cubes 1. You can probably figure this one out. From 9 cubes with a z translation of 2.5. And I'm going to create 9 cubes 2 from 9 cubes with a z translation of a minus 2.5. And then I'm going to assemble 9 cubes 1, 9 cubes 2 into Rubik's Cube, right? Okay? And now when I'm done, I've got, when I was over there at that other blackboard, you guys kind of said, oh, big deal, he did a cube. Right, now I've got 162 cubes in here, I think. Okay? Now 162 squares, right, in here. 162 polygons in these files. And using commands of this type with these polygon files, you can build up objects really quickly. You can transform them around because you're just transforming all the coordinates. Right? So you can get these transform commands and transform things around, etc. Now if I go back here to this other blackboard, you can kind of see that up here, if I look at cube has some things underneath it here, right? That it has square, right, down here. Here's cube. And then I have back, left, right, bottom. Right? All of whom, here's bottom. And here's left, right, and back. All of whom reference square. Okay? And then over here, because I created top from bottom, right, I have to have top up here. Right? Cube also has a top, which is not created from square, it's created from bottom. And you can kind of see that this is a graph, a directed graph, okay? And it kind of looks like we kind of associate these things sometimes with a tree, okay? It almost looks like a tree if I duplicate square a whole bunch of times down here at the bottom, okay? But each one of these things, the original square contains the polygonal points, and what back is really a transformation, right? What this node really has is a transformation in it. Okay? It really has a transformation. And what I can do is I can build up these trees with transformations, or these tree-like structures, graph-like structures, with transformations at each node, which take the original points here and help me put them together up above. Okay? Over here, what I have is a big mess. Okay? I have Rubik's Cube here. And I have three things underneath it. 9 cubes, 9 cubes 1, 9 cubes 2. And then I have three things under here, right? Which are the 3 cubes you can think of under each 9 cubes, if you wish. All the way down, and I can get all the way down to the bottom, of which I've got cubes, right? And so the difference is that we have at each one of these steps, we have all of these things which have transforms at them. And they transform the original things down here at the bottom, okay? But, they can really be saved as files, etc. And this is called a hierarchical modeling system. It's called a hierarchical modeling system. And what we do is we define a few simple objects down at the bottom, and then we combine them together into much bigger objects up at the top. You can kind of envision in your head of starting with a cube, a little cube, 1 unit on a side, and you could transform that into a table leg. Okay? You could transform this cube into a table leg. You can create 3 other table legs in different positions, right? You can take that cube, expand it out to get the table top, right, etc. That you could all basically build these things from one entity. And that's always our idea in graphics, is we want to build things from very few entities, right? So we define these very few entities, and then we transform them around, right? So that almost every entity we have has one or more transforms associated with it. And the thing to look at that is really interesting The one that's really interesting and hard are those people that model human beings, okay? Because between every joint there is something to model, okay? And that something has a transform associated with it. Now it happens to be pinned to a joint, right? It has a transform associated with it. But when this arm moves, right, when the upper arm moves, the lower arm has to go with it. It can't just stay. Right, so these transforms are built up hierarchically. And anybody that has, if you go take Dr. Neff's class here on character animation over in the art department, he will show you characters, right, that they've built. And they build them basically one component at a time, and they build them up hierarchically. So you can turn the entire upper torso of the body, for example, by using one transform. And that it affects everything in the body. So you should envision these things, these large things, as big trees after a while. When you're going to do Kemper Hall, you should envision it as a big tree of things that you're going to put together. Okay? And the things at the bottom are the low-level polygons. So to make those chairs, you've got to make a chair arm, you've got to make, a frame, you've got to do other things for those chairs. Once you've made one, you've made them all. Okay? And so you can replicate them around. Once you've made these floors here, linoleum floors are actually really easy. Right? All you need to do is you need to make, if you go over in Kemper Hall and you look at the linoleum floor in Kemper Hall that looks like that tries to set off all these things, seizures and all in your brain as you walk down the hallway. Okay? The thing about these floors, they all have a very simple pattern. All you need to do is make up 4 different squares and put them in this pattern, and you've got the entire hallway. Okay? There's actually, by the way, there's different patterns on each one of the floors of Kemper, right? And the algorithm is extremely simple. All I've done in each one of the floors is removed one of the color tiles and replaced it by another. Okay? That's all they've done. And you can, if you go over toward the elevators on the far wing, there's a channel that goes all the way down from the elevators, and it was originally put in there to lower equipment into the building. But you can lean out and you can see all the patterns on all the floors, right, in Kemper. And you can see the algorithm immediately when you see all the floors in that way. Okay? So a lot of these things, if I want to model this room, all I have to do is model one chair. I'm done. All I have to do is model one table. I have to model with these speakers, right, or these microphones. I have to model a flexible neck, and the rest is the same. Okay? The flexible neck is going to be something called a Bezier curve, right, when I get done, right, or something like that. But what I need you to realize with these larger things that you need to do is that everything we have is all done by modeling one thing, right, spending our time on one thing, and then replicating it over and over and over and over and over again. Okay? You should go back and look at the original Toy Story movie. The thing that blew everybody away in the Toy Story movie was the chase, okay, down the street. Because what blew everybody away was that animators could do the chase, but the backgrounds in that chase were incredibly well detailed, and they were going by very fast, right? But they were the houses were all incredibly well detailed. Normal animation firms do hand animation could never have attempted that. They would have just made it all blurry in the background. But these people could actually model the houses themselves. However, when you go down the street and you're chasing down the street, and if you look in the background, which we all did when we looked at the movie, right, you notice that there aren't very many houses, right, different, right? They modeled like 3 of them. Okay? And they just kept repeating the same houses over and over again in the background. It looked great, okay, but they just kept repeating the same houses in the background. Okay? And, when it's fun going to these movies with computer graphics people because we notice things that other people don't in the movies. But so, one of the things to do when you're modeling these big structures like this is think of what's the same, right? What can I do here that's the same? Where all I have to do is transform them. Right? We have transform routines. You've all discovered push and pop probably now, right? And all you need to do is push the transform stack, put a new transform on for the thing you want, pop the stack when you're done, right? And it draws it. So all you need to do then is figure out how to transform these things around to make them look right. Okay? And I won't make you do all the computers that they have in that thing there, but that's okay. So, okay, is this kind of clear? This is a system called Midas. Okay, it was invented in 1977 by a guy at the University of Colorado, and it was copied by almost everybody for a while. And it still is the core of many of these systems, is that we set things up with polygons, we set them up with transforms. Usually when you look at these things, they don't have just points in them, they have colors, they have material properties, they have texture coordinates, they have all kinds of things in them also, not just points. But all of these things can be manipulated by transforms, right, etc. And basically you just have these set of functions that act on these files that do various things. And if anybody comes up to my office, I'll show you my railroad cars that we did with these systems. And actually it was not as big of a project as you might think to do some of these things. But you know, these are good. And then you typically there's what, four basic commands here. Okay. You start expanding these commands. The little system that I have, which I still call Midas, has about 120 different commands on it. Okay. One of which, for example, is a volume of revolution command, of which it takes a polygon and revolves it around an axis, okay, to make a volume of revolution. Well, there's nice commands I can use in OpenGL to do that, right? And there's other things I can do if I want also, where I can rotate them around in segments, right, and then have very few segments. So volumes of revolution I can actually keep in here. I have Bezier patches and Bezier curves, which we'll get into in the next assignment to do. So all of these things are all possible in such a little system. But what you can do is, it looks pretty boring at first when you start writing these things up, and then all of a sudden you create thousands and thousands of objects really quickly. Okay. And one of the early computer graphics class things was to do a Rubik's Cube and actually be able to manipulate it so that it actually solved. Okay, and doing the transforms to manipulate all the sides is an interesting exercise. Okay, to make sure all the subcubes go in the correct places. And you see all kinds of really interesting things where the cubes go all different wild directions and come back together, and you know, and things like that. These things. So okay, I'm done for today. Question? I have a question.
What about the colors? Because you haven't mentioned so the Rubik's Cube app.
Yeah, everything's built out of the same thing, but one of the commands we have here is a color command. And I say color this file such and such, and it'll go in here and it'll put the RGB values of a base color in there. Right, so we have color commands right along with the rest of them. We also have texture commands. We also have many other things. There are other transforms besides these elementary ones too. There's a warp type transform that looks a lot like the viewing thing you do. And a warp type transform takes a cube and makes it into one of these. It's kind of a beveled button. Takes a cube, and now that kind of what things you all should know. That's kind of what cubes look like in image space, right? They bevel themselves like this. These beveled buttons are actually quite easy. Once in the class, I gave everybody. I told them they had to make an HP calculator. Pocket calculator, right, where you could touch the buttons and it did the right thing. Okay, and the HP Pocket Calculator, the buttons are beveled, and we want to know how to make beveled buttons. And most of us just figured out these 5 polygons. One student actually figured out a bevel command from the image space thing and actually beveled it, and then found it in image space, translated it back to the correct spot so it appeared on the calculator correctly, which was kind of interesting. Right. So okay, so you're beginning. Well, one thing about graphics is not only drawing things; it's also building things. And you know, these are the two of the problems that we always come up with. We can draw them, we can build them. So, and next time I'll do this scan conversion process for you, which is kind of the lowest level thing that we do, but you kind of have to figure it out. And it actually is pretty easy. And it's about the lowest level thing we do just before we draw things. And so, okay, I'm done.